Chapter 8. The Art of Becoming. Quote, "No more fiction for us. We calculate, but that we may calculate, we had to make fiction first." Nietzsche. Returning now to irrationals, I shall endeavor to show the close connection that exists between this problem and the problem of continuity which I discussed in the preceding chapter. But first let me resume the situation where I left it before taking up the problem of continuity. The attempt to apply rational arithmetic to a problem in geometry resulted in the first crisis in the history of mathematics. The two relatively simple problems, the determination of the diagonal of a square and that of the circumference of a circle, revealed the existence of new mathematical beings for which no place could be found within the rational domain. The inadequacy of rational arithmetic was thus forcefully brought home. A further analysis showed that the procedures of algebra were generally just as inadequate, so it became apparent that an extension of the number field was unavoidable. But how was this to be accomplished? How can an infinity, nay, an infinite variety of infinite collection of irrationals, be inserted into the closely knit texture of the rational aggregate of numbers? We must recast the old number concept, so much is certain. And since the old concept failed on the terrain of geometry, we must seek in geometry a model for the new. The continuous indefinite straight line seems ideally adapted for such a model. Here, however, we strike a new difficulty. If our number domain is to be identified with the line, then to any individual number must correspond a point. But what is a point? We must have, if not a definition, at least a clear-cut idea of what we mean by an element of a line, a point. Now, the general notion of a point as a geometrical being without dimension is, of course, a fiction. But when we analyze this fiction, we find that back of it are three distinct ideas. In the first place, we conceive the point as a sort of generating element, which in its motion describes the line. This idea seems to fit best our intuitive idea of continuity, which is the first attribute we ascribe to the line. When, however, we attempt to take this dynamic conception as a basis for the analogy between the line and the number domain, we find the two incompatible. Indeed, our senses perceive motion as something individual, indivisible, uninterrupted. The very act of resolving motion into elements results in the destruction of the continuity which we have resolved to preserve. For the sake of number, it is necessary to regard the line as a succession of infinitesimal resting stations, and this is repugnant to the very idea of motion conceived by us as the direct opposite of rest. Therein lies the force of Zeno's arguments. We saw how the mathematician tried to bridge the discrepancy by the invention of the infinitesimal analysis. We saw how this analysis, starting with geometry and mechanics, succeeded in acquiring a dominant position in every field of the exact sciences until it became a veritable mathematical theory of change. Speaking pragmatically, this sweeping triumph of analysis is sufficient proof of the validity of its methods. But while it may be true that the proof of the pudding is in the eating sheds no light on what a pudding is. The very success of analysis only accentuates the age-old question, what constitutes a continuum? In the second place, the point may be regarded as an intersection of two lines, i.e., as a mark left on the line in question by another line. As such, it is just a partition, a manner of severing the line into two mutually exclusive complementary regions. It is this idea which Richard Dedekind took as a point of departure in his epoch-making essay entitled Continuity and Irrational Numbers, which appeared in 1872. Of this I shall tell in the next chapter. Finally, we may regard the point as a limiting position in an infinite process applied to a segment of a line. This process may take many forms. For the present, it is sufficient to say that a typical instance is the dichotomy of the Greeks. The arithmetical counterpart of the infinite process is the infinite sequence, and it is the rational infinite sequence that George Cantor uses as the vehicle for his famous theory of irrationals, which was first published in 1884. It is this simple and far-reaching idea that is the subject of this chapter. A sequence is rational if its terms are all rational numbers. It is infinite if every term in it has a successor. A set of operations generating an infinite sequence I shall call an infinite process. The prototype of all infinite processes is repetition. Indeed, our very concept of the infinite derives from the notion that what has been said or done once can always be repeated. When repetition is applied to a rational number a, we obtain the repeating sequence a, etc. I shall say that this sequence represents the number a. Another fundamental operation, which I shall call the serial process, is that of successive addition. Given the sequence a, b, c, d, e, f, g, etc., the serial process creates a new sequence, a plus b plus c, a plus b plus c plus d, etc., which we call the series generated by the sequence a, b, c, etc. Thus, from the repeating sequence 1, 1, 1, etc., we derive the natural sequence 1, 2, 3, 4, etc. The serial process can obviously be applied to any sequences, and therefore to every sequence corresponds a series. Of the greatest importance, however, are those series which are generated by evanescent sequences. These latter are characterized by the gradual diminution of the successive terms, so that it is possible to go out sufficiently far to find terms less in value than any assignable number. Of this type are the sequences 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, etc., and 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, etc. Now, given any two sequences, a third sequence can be formed by subtracting one from the other term by term. It may happen that the different sequence so derived is evanescent, as is the case with the two sequences 2 over 1, 3 over 2, 4 over 3, 5 over 4, 6 over 5, 7 over 6, etc., and 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7, etc. Here the sequences between corresponding terms form the sequence 3 over 1 times 2, 5 over 2 times 3, 7 over 3 times 4, 9 over 4 times 5, 11 over 5 times 6, 13 over 6 times 7, 15 over 7 times 8, etc. The denominator of each term is the product of two successive numbers, and the numerator is the sum of the same numbers. The 1,000th term of this sequence is less than 0.002. The 1,000,000th is less than 0.000002, etc. The sequence is certainly evanescent. I shall call two sequences whose difference is evanescent asymptotic. Now, one of the two asymptotic sequences may be a repeating sequence, as for instance in the case of 1, 1, 1, 1, etc., 1 over 2, 2 over 3, 3 over 4, 4 over 5, etc. The repeating sequence represents the rational number 1. I shall say that the second sequence, asymptotic to the first, also represents the number 1, or that it converges towards 1 as a limit. It stands to reason that if two sequences are asymptotic to a third, they are asymptotic to each other. And furthermore, if one converges to a certain rational number as a limit, the same is true of the other. Now, since this is so, a great number of sequences may, in spite of their difference in form, represent the same number. And such is indeed the case. Thus, the number 2 is capable of an infinite number of representations by rational sequences, of which a few are 1.9, 1.99, 1.999, 1.99999, etc., 2.1, 2.01, 2001, 20,001, etc., 1 1/3, 1 2/3, 1 3/4, 1 4/5, etc., 1 1/2, 1 3/4, 1 7/8, 1 and 15 over 16, etc. The same is true of any rational number. In particular, any evanescent sequence may be regarded as a representation of the rational number 0. The simplest type of sequence, and one that is at the same time of great historical and theoretical importance, is the geometrical sequence. Here, having selected any number for the first term and any other number for ratio, we proceed from term to term by multiplication through the ratio. Any repeating sequence may be regarded as a special geometrical sequence, the multiplying ratio here being 1. If we eliminate this trivial case, we can classify geometrical sequence into increasing and diminishing. Examples of these are 2, 4, 8, 16, 32, 64, etc. to 2 to the exponent n, and 1, 1/3, 1/9, 1 over 27, 1 over 81, etc., where 1 over 3 is to the exponent n. In the increasing geometrical sequence, the terms grow indefinitely in absolute value. That is to say, if we go out far enough, we can find terms which exceed any assignable number, no matter how great. Such sequences are said to diverge. The diminishing sequence is always evanescent, and for this reason is of special interest to us here. But what makes it particularly valuable is the fact that the series generated by such an evanescent geometrical sequence will always converge towards a rational limit, and that conversely any rational number can be regarded as the limit of some rational geometrical series. Moreover, here we have one of the rare cases where the sum of a series can actually be evaluated in terms of the immediate data. The series generated by a geometrical sequence is called a geometrical progression. An evanescent geometrical sequence generates a convergent progression. If the sequence begins with the term a and has r for ratio, the limit is given by the simple formula s equals a over 1 minus r. This limit is called the sum of the progression. The dichotomy sequence in the first argument of Zeno is the geometrical progression 1 over 2, 1 over 4, 1 over 8, 1 over 16, etc., and it generates the series 1 over 2, 3 over 4, 7 over 8, 15 over 16, etc. This latter converges towards 1, as can be seen directly or by the summation formula. The sum 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus etc. represents the finite number 1 in spite of the argument of Zeno that this sum is extended over an infinite number of terms. The introduction of the concepts of convergence and limits may be objected to on one ground or another, but once accepted, the argument of Zeno that a sum of an infinite series of numbers must by necessity be infinite loses its force. The second Zeno argument also involves a geometrical progression. To deal with it concretely, let us assume that Achilles advances at the rate of 100 feet per minute, and the tortoise at the rate of 1. When will Achilles overtake the tortoise if the original handicap was 990 feet? Never, says Zeno. Common sense tells us, however, that Achilles gains on the tortoise 99 feet per minute, and that the original distance of 990 feet will be wiped out at the end of the first 10 minutes. But let us argue in the Zeno fashion. By the time Achilles reaches the position originally held by the tortoise has advanced 1/100th of the handicap, or 9.9 feet. By the time Achilles arrives at this second position, the tortoise has advanced 1/100th, or 0.099 feet. But what was said once can always be repeated. The handicap is being reduced in the geometrical progression 990, 9.9, 0.099, 0.00099, etc., the sum of which by the summation formula is 1,000. Achilles will have covered 1,000 feet before overtaking the tortoise, and this will take him 10 minutes. Again, the sum of an infinite number of terms may be finite. Periodic decimal fractions are but geometrical series in disguise. Consider, for instance, the infinite decimal fraction, which is of the pure periodic type 0.36363636, etc. I shall write this short 0.36. The actual meaning of this is 36 over 100 plus 36 over 10,000 plus 36 over 1 million, etc. This, however, is a geometrical series of ratio 1 over 100, and the summation formula shows that the series converges towards the rational limit 36 over 99, or 4 over 11. The same is true of a so-called mixed periodic fraction, such as 0.34, bracket 53, bracket. For instance, for multiplying this by 100, we obtain the pure periodic fraction 34 to the exponent 53 over 99. And since the mixed periodic fraction is 1 over 100 of this, we have 0.34 bracket 53 bracket, which equals 3,419 over 9,900. Even a terminating fraction may be regarded as a periodic fraction of period 0. For instance, 2.5 equals 2.50000, etc., which equals 2.5 bracket 0 bracket. Now we were taught in school how to convert any common fraction into a decimal. The procedure is called long division, and we know by experience that it leads either to a terminating fraction, as in the case of 1/8, which is equivalent to 0.125, or to an infinite periodic, as in the case of 1/7, which is represented by 0.142857 bracket. This property can be proved in all rigor and may be formulated in the statement, any rational number can be represented in a unique way as an infinite periodic decimal fraction. Conversely, any periodic decimal fraction represents a rational number. On the other hand, we can obviously construct any number of decimal sequences which, while infinite, are not periodic. The distribution of the digits may be chaotic, or it may follow a regular yet non-periodic law. Such, for instance, is the case of the decimal series 1.101112113, 192021, 100101, etc. If we could find a repeating rational sequence A, etc., which would be asymptotic to this decimal sequence, then this latter would represent the rational number A. But we know that this is impossible, for if it were possible, the sequence would be periodic, and such is not the case. What then does this series represent? We do not know. The manner in which we defined convergence and limit precludes all possibility of classifying the sequence as a number. And yet there are our intuitive notions of convergence and of limit, as of something growing and yet never exceeding a certain magnitude, or as of something waning and yet never falling below a certain magnitude. From this intuitive viewpoint, the infinite non-periodic decimal series does converge, and the same is true of many other sequences, such as 1 1/2 to the exponent 2, 1 1/3 to the exponent 3, 1 1/4 to the exponent 4, 1 1/5 to the exponent 5, etc., which incidentally represents the transcendental E. It is this naive idea of convergence and limit that was accepted as axiomatic in the early days of analysis, and it must be admitted that, in spite of the pitfalls to which it led, it is to this idea that the calculus owed its first successes. Thus, the questions which present themselves most naturally to the mind are these. Is it possible to clothe this vague intuitive idea of convergence and limit in a precisely formulated definition? Is it possible by such a definition to create a new instrument which will permit us to deal with these new mathematical beings, exhibited by the non-periodic decimal series and other sequences with the same certainty as when dealing with the special kind which admit rational limits? To answer these questions, we must examine whether among the properties of the special sequences which converge towards rational limits there exists one, which would permit of an immediate generalization to the vastly more extended kind which do not so converge. George Cantor discovered such a property in what I shall call the self-asymptotic nature of a convergent sequence. To exhibit this, let us consider again the dichotomy series. Let us advance this sequence by curtailing the first term and making the second term first, the third second, etc. This advancing process will create the succession of sequences 1/2, 3/4, 7/8, 15/16, 31/32, 63/64, 127/128, etc., 3/4, 7 over 8, 15 over 16, 31 over 32, 63 over 64, 127 over 128, 255 over 256, etc. And 7 over 8, 15 over 16, 31 over 32, 63 over 64, 127 over 128, 255 over 256, 511 over 512, etc., which obviously can be continued indefinitely. Now, even a casual examination of these sequences shows that they are all asymptotic to each other, that is, that the difference sequence formed with any two is evanescent. It can be shown that this self-asymptotic property holds for all those sequences which converge towards a rational limit, but it is by no means confined to these. In fact, any infinite non-periodic decimal series has also the same property. Indeed, consider as an example the decimal series 0.1011112131415, etc., which can be written as 0.1, 0.10, 0.101, 0.1011, 0.10111, 0.101112, etc. It is obvious that curtailing any number of these rational approximations will not affect even the appearance of the sequence. Thus, we can write it in the form 0.101112, 0.101121, 0.10111213, 0.1011112131, etc., which is certainly asymptotic to the first. And so Cantor extended the idea of convergence, which hitherto applied only to those sequences which were asymptotic to some rational repeating sequence, by identifying the two terms self-asymptotic and convergent. Moreover, he extended the idea of limit by regarding the self-asymptotic sequence as generating a new type of mathematical being, which he identified with what had long before him been called real number. Now, applying the name number to such beings would be justifiable if it could be shown that all the stipulations of the principle of permanence were satisfied. That the first stipulation is satisfied follows from the fact that among the convergent sequences there are those which admit rational numbers for limits. The second stipulation implies the criteria of rank. Let us then consider two sequences A and B which define the two real numbers A and B, and let us form the difference sequence A minus B. It may happen that this latter is evanescent, in which case A and B are asymptotic, and we say then that the numbers A and B are equal. As an example of this, take the two sequences 1 1/2 to the exponent 2, 1 1/3 to the exponent 3, 1 1/4 to the exponent 4, 1 1/5 to the exponent 5, etc., and 2 plus 1 over 2, 2 plus 1 over 2 plus 1 over 3, etc., 2 plus 1 over 2 plus 1 over 3 plus 1 over 4, 2 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. These can be proved to be asymptotic and therefore represent the same real number, which is the transcendental E. If the difference sequence is not evanescent, then it may happen that, beginning with a certain term, all terms are positive, in which case we say that the sequence A dominates the sequence B, or that the real number A is greater than the real number B. And again, if beginning with a certain term all the succeeding terms of the difference sequence are negative, then A is dominated by B, and we then say that A is less than B. These criteria, it can be shown, reduce to the standard when A and B admit rational limits. Finally, we define the sum and the product of two real numbers as the real numbers defined by sequences obtained by adding or multiplying the corresponding terms of these sequences. This, of course, implies that these resultant sequences are themselves convergent, and that such is indeed the case can be proved in all rigor. Furthermore, it can be shown that addition and multiplication so defined are associative, commutative, and distributive. From the standpoint of the principle of permanence, these new magnitudes can therefore be admitted as full-fledged numbers. By their adjunction, the rational field becomes but a province in a vastly more extensive realm, which we shall call the domain of real numbers. Will this new domain contain the irrationals of algebra, the transcendental of analysis? Yes, and to exhibit this, let us return to the equation x squared equals 2, which over 2,000 years ago, in the guise of the problem to determine the diagonal of a square, precipitated the crisis which has now culminated in the erection of the real number domain. We were taught in school an algorithm for the extraction of the square root. This procedure gives for what we call root 2 a set of rational approximations which form the convergent sequence 1, 1.4, 1.41, 1.414, 1.4142, 1.41421, etc. This sequence has no rational limit, but the sequence obtained by squaring each term in it, namely 1, 1.96, 1.9881, 1.999396, etc., converges towards the rational number 2. Therefore, when we say that the positive solution of the equation x squared equals 2 is the sequence in question and denote the number defined by it root 2, we mean not only that the sequence of squares converges, but that it belongs to that rare type of convergent sequences which possesses a rational limit, in our case the number 2. In other words, the sequence represents root 2 because we admit that the number 2, while not a perfect square, is the limit towards which a sequence of perfect squares converges. A similar procedure will apply to other algebraic or transcendental equations. The actual discovery of an algorithm, which would in any particular instance generate the sequence that converges towards the sought solution, may be a matter of considerable mathematical difficulty. Yet, once devised, the sequence can always be paraphrased into an infinite decimal fraction which by its very nature is convergent, and, therefore, represents a real number. Thus, the admission of the validity of infinite processes takes us out of the restricted boundaries of rational arithmetic. It creates a general arithmetic, the arithmetic of real numbers, and this furnishes us with the means of attacking problems before which rational arithmetic stood powerless. It would seem at first that by giving the very general name real to the limits of rational sequences we lacked foresight, for indeed it is only natural now to consider infinite sequences of such irrationals. If we had called the first type irrationals of the first rank, these new limits would then be called irrationals of the second rank. From these we would derive irrationals of the third rank, etc., etc. That this is no idle juggling is testified by such a simple expression as root 1 plus root 2, the direct interpretation of which creates the irrational sequence root 2.4, root 2.41, root 2.414, etc. Yet in this case at least the objection is unfounded, for if we denote root 1 plus root 2 equals x, a simple algebraic manipulation will show that x is a solution of the equation x to the exponent 4 equals 2x squared plus 1. To this, however, a procedure similar to the algorithm of root extraction could be applied, and this would permit us to construct a set of rational approximations, which in turn would exhibit root 1 plus root 2 as a rational sequence, asymptotic to the irrational sequence which we first considered. Now, strange though it may seem at first, this is a most general fact. To any irrational sequence we can assign a rational sequence, and usually more than one, which is asymptotic to it. So that the introduction of ranked irrationals, interesting though these latter may be from the purely formal standpoint, is quite superfluous as far as general arithmetic is concerned. The proposition that whatever can be expressed by means of an irrational sequence is susceptible of representation by means of a sequence of rational numbers is of fundamental importance. It assigns to rational numbers a special role in the theory. Inasmuch as any real number can be expressed by infinite convergent rational sequences, the rational domain, reinforced by the concepts of convergence and limit, will suffice to found arithmetic. And through arithmetic, the theory of functions, which is of the cornerstone of modern mathematics. But this capital fact is of just as great importance in applied mathematics, since any rational sequence can be represented as an infinite decimal series. All computations may be systematized. By limiting himself to a certain number of decimal places, the computer may obtain a rational approximation to any irrational or transcendental problem. And what is more, the degree of accuracy of this procedure not only can be readily estimated, but even assigned in advance. When Louis XIV was asked what was the guiding principle of his international policy, he is reported to have answered cynically, "Annexation." One can always find a clever lawyer to vindicate the act. I am always reminded of this anecdote when I reflect on the history of the two problems, the infinite and the irrationals. The world did not wait for Weierstrass and Cantor to sanctify the procedure of substituting for an irrational number one of its irrational approximations, or, what is the same, of replacing the limit of an infinite sequence by an advanced term in the sequence. It measured its fields and erected its structures. It dug its tunnels and built its bridges. It wrought its arms and designed its machines on rational approximations, asking no questions as to the validity of the principle involved. I spoke before of the approximate values which Theon and Hero gave for the square roots of integers. There are indications that the problem is of older origin and probably goes back to the early Pythagoreans. But it was Archimedes who first made the systematic applications of the principle. Let us return again to the classical problem of squaring the circle, in which are so well reflected the various phases through which mathematics passed. As I have already mentioned, Archimedes' method consisted in regarding the circumference as contained between two sets of regular polygons, one set inscribed, the other circumscribed to the circle. Starting with hexagons, he kept on doubling the number until polygons of 96 sides were reached. The successive perimeters of the inscribed polygons form one sequence, and those of the circumscribed form another. If the process be continued indefinitely, the two sequences would converge towards the same limit, the length of the circumference. If the diameter of this latter be unity, the common limit is pi. What is remarkable about these sequences is that they are both irrational. Indeed, the first terms of the first are 6, 6, bracket, root 6 minus root 2, bracket. The first terms of the second, 4, root 3, 4 times root 3, and 24, bracket, 2 minus root 3, bracket. And the succeeding terms involve radicals of increasing complexity. These irrational sequences Archimedes, in full confidence, replaced by rational, and in this manner deduced that pi was contained between the two rational numbers 3 and 1/7 and 3 and 10/71. The same two classical problems, the radicals and the evaluation of pi, gave the impetus for the development of another important infinite process, the continued fraction. Though some historians of mathematics maintain that these were already known to the Greeks, the first record of continued fractions which have reached us is found in a book of Bombelli dated 1572. He says, however, that many methods of forming fractions have been given in the works of other authors, the one attacking and accusing the other without due cause, for, in my opinion, they are all looking to the same end. Judging by this, the algorithm must have been known early in the 16th century. The same end of which Bombelli speaks is the finding of rational approximations for radicals. I shall illustrate the method on root 2. This number being contained between 1 and 2, let us set root 2 equals 1 plus 1 over y. From this, we draw that y equals 1 plus root 2 equals 2 plus 1 over y. Continuing this way, we obtain the fraction root 2 approximately equals 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, and so on. This is a special type of continued fraction. It is called simple because all the numerators are 1, and periodic because the denominators repeat. If we limit ourselves to one element, 2 elements, 3, etc. of a continued fraction, we obtain a set of rational approximations, which are called convergents. In the case of root 2, the convergents are 1, 1 and 1/2, 1 and 2/5, 1 and 5/12, 1 and 12/29, 1 and 29/70, 1 and 70/169, etc. Two features make continued fractions particularly valuable. In the first place, a simple continued fraction always converges, and in the second place, it has an oscillating character. In fact, we can break up the convergence into two groups by taking the first, third, fifth, etc., then the second, fourth, sixth, etc. In the case of root 2, we obtain the two asymptotic sequences, 1 and 2/5, 1 and 12 over 29, 1 and 70 over 169, etc., and 1 and 1/2, 1 and 5 over 12, 1 and 29 over 70, 1 and 169 over 408, etc. The first is continually increasing and has root 2 for upper bound. The other is continually decreasing and has root 2 for lower bound. This oscillating feature makes continued fractions invaluable for accurate approximations, for the error committed in stopping at any convergent can be readily estimated. In the 18th century, Euler showed that any quadratic irrationality can be represented by a simple periodic continued fraction, and soon afterward Lagrange proved that the converse is true, i.e., that any such periodic fraction represents a solution of a quadratic equation. Thus, the periodic continued fractions play the same role with respect to the quadratic equation as the periodic decimal fractions with regard to the linear equation. The procedure we established for root 2 can be applied to any equation, so that any real solution of the most general equation may be represented as a continued fraction. Yet only in the case of the quadratic equation will the fraction be periodic. It would seem at first that continued fractions are peculiarly adapted to algebraic manipulations. If this were so, then we would have some criterion for distinguishing algebraic irrationals from transcendentals. Now, insofar as the algebraic origin of the fraction imposes certain limitations on the magnitude of its elements, this is true, and as a matter of fact, it was this limitation that enabled Louisville to discover the existence of non-algebraic numbers. But apart from this, the procedures of algebra occupy no privileged position either with regard to continued fractions or, as far as we know, with regard to any other type of sequence. It is this remarkable indifference of infinite processes to algebra which is responsible for the great difficulties encountered in the theory of transcendentals. Thus, for instance, the transcendental numbers pi and e can be expressed in rather elegant fashion by continued fractions, as the reader can glean from the table at the end of this chapter. The expansion of pi into a continued fraction was discovered by Lambert in 1761 and is of great historical importance. The non-periodicity of this fraction shows conclusively that the number pi is not a root of a quadratic equation with rational coefficients. This suggests that the quadrature of the circle cannot be achieved by straight edge and compass alone. I say suggests, not proves, for the number pi may still be a root of a quadratic equation, the coefficients of which involve quadratic irrationalities only, in which case the continued fraction would be non-periodic, but a straight edge compass construction possible. There is a remarkable analogy between simple continued fractions and infinite decimal series. In the first place, both types of sequences are always convergent, i.e., any random law of succession of denominators of a continued fraction or digits in a decimal fraction will always represent a real number. In the second place, if the law of succession is periodic, the decimal series represent a rational number, while a periodic continued fraction represents a quadratic irrationality, i.e., a number of the form a plus root b, where a and b are rational. Finally, any real number can be represented either in the form of a decimal series or as a continued fraction, provided that common fractions be regarded as a special case of continued. These properties single out these two types of infinite processes as particularly adapted for the representation of real numbers, and yet the history of infinite processes revolved about a procedure which was much more general in its scope, and which at the same time, because of its very generality and vagueness, led to a number of perplexing and paradoxical results. No doubt the origin of this procedure was the geometrical series, which, if we are to judge from Zeno's arguments, was already known to the ancients. When we restrict ourselves to positive geometrical series, we see that the series is convergent when the ratio is less than 1, divergent otherwise. This result can be immediately generalized to alternating geometrical series, i.e. to the case when the ratio is negative. The alternating geometrical series, too, will converge if the ratio is a proper fraction, will diverge otherwise. An interesting case, however, arises when the ratio is equal to -1. The series is then the form a minus a plus a minus a plus a minus a plus a minus a plus etc. We would say today that this series diverges in spite of the fact that the sum never exceeds A. Indeed, this series can be paraphrased into the sequence A-O, 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 etc., and this has no definite limit. However, Leibniz thought otherwise. He argued that the limits A and O are equally probable, and maintained that the sum approaches the mean value 1/2 A as a limit. The tract in which Leibniz deals with series appeared late in the 17th century and was among the first publications on the subject. Characteristic of this early history of series is that the question of their convergence of divergence, which today is recognized as fundamental, was in those days more or less ignored. So, for instance, it was generally believed that if the sequence generating a series is evanescent, the series is necessarily convergent. This, as we saw, holds for geometrical series, and no doubt such was the origin of this widespread error. It was not until the publication of Jacques Bernoulli's work on infinite series in 1713 that a clearer insight into the problem was gained. The occasion was the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc. The generating sequence being evanescent, it was generally held that this series converges. Bernoulli, however, gives in his book a proof, due to his brother John, of the fact that this series slowly but surely diverges. Bernoulli's work directed attention towards the necessity of establishing criteria of convergence. The evanescence of the general term, i.e. of the generating sequence, is certainly a necessary condition, but this is generally insufficient. Sufficient conditions have been established by D'Alembert and Maclaury, Cauchy, Abel, and many others. I shall not dwell on this subject, which is foreign to my general purpose. However, I must state that to recognize whether a series converges or not is even today rather difficult in some cases. There is, however, a special type of series which was in the early days a matter of considerable interest, and in which the evanescence of the general term is a criterion of convergences. These are the so-called alternating series, typical of which is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus etc. This series converges towards the so-called natural logarithm of the number 2, the approximate value of which is 0.639. And yet, the series of absolute values is the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc., which, as we stated, diverges. Now, the reason I mention this type of series is that it was responsible for a number of perplexing incidents. The general attitude towards series during the 17th and 18th centuries was to consider them not as special types of sequences, but as sums of an infinite number of terms. It was, therefore, natural to attribute to this addition the properties of the finite operation, i.e. associativity and commutativity. Thus, it was assumed that, the sum being independent of the arrangement of the terms, it was permissible to rearrange the terms at will. Now, in 1848, Lejeune Dirichlet proved that such is indeed the case with a convergent series of all positive terms. If, however, the series has negative terms, then two cases may arise. If the series is absolutely convergent, i.e. if the series of absolute values converges, then associativity and commutativity do hold. If, however, the series is only conditionally convergent, i.e. the series of positive terms diverges, then these properties break down. And then, as a matter of fact, by a proper rearrangement of the terms, it is possible to deduce that the sum equals any number whatsoever. The natural logarithm of a number a is given by the exponent x in e to the exponent x equals a, and x equals log a. Where e is the transcendental, which was mentioned before on several occasions, the approximate value is e equals 2.71828. Small wonder, therefore, that before the days of Dirichlet, many weird results were arrived at through manipulating series, particularly of the series which we called conditionally convergent. A historical example of the harmonic series. Let us denote by x the sum of its odd terms, and by y that of the even. Then we can write y equals 1 plus 1/2 plus 1/4 plus 1/6, etc. equals 1/2 bracket 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus etc. bracket, from which we carelessly draw y equals 1/2 bracket x plus y bracket, or 1/2 x equals 1/2 y, or x minus y equals 0. We reach the fallacious conclusion that the alternating harmonic series converges towards zero when, as a matter of fact, the series approaches the natural logarithm of 2 as a limit. Although today such arguments would appear absurd enough, they were quite common not only in the 18th century but even in the early part of the 19th. Thus, as late as 1828, Abel, in a letter to his former teacher, Holmboe, complains, quote, "The divergent series are the invention of the devil, and it is a shame to base on them any demonstration whatsoever. By using them, one may draw any conclusion he pleases, and that is why these series have produced so many fallacies and so many paradoxes. I have become prodigiously attentive to all this, for with the exception of the geometrical series, there does not exist in all of mathematics a single infinite series, the sum of which has been determined rigidly. In other words, the things which are the most important in mathematics are also those which have the least foundation. The most of these things are correct in spite of that is extraordinarily surprising. I am trying to find a reason for this. It is an exceedingly interesting question." End quote. Abel's letter already breathes a new spirit. It was the dawn of a new era, the critical era in mathematics. The naive attitude which had reigned since the beginning of the revival of learning was coming to an end. Tremendous conquests had been made in every field of the mathematical sciences. It became necessary now to consolidate these results into systems, and above all, it was necessary to examine with care the foundations on which these systems were to rest. To tell the story of infinite processes since Cauchy and Abel is to tell the story of modern analysis and theory of functions, and this is beyond our scope. But this sketchy presentation of the early history of infinite processes will suffice to show that the Cantor theory of irrationals was but the consummation of a long historical evolution, an evolution which began with the Pythagorean crisis, which was temporarily interrupted when the progress of all ideas was arrested, only to be resumed with the revival of learning. As in the case of analysis which I presented in the last chapter, the guiding motive throughout this long period of groping was a sort of implicit faith in the absolute nature of the unlimited. This faith found its supreme expression in the finale, the new theories of the continuum, of which I am about to tell.